Hello, everybody. So this is C++20 Ranges in Practice. My name's Tristan. I will be your host for the next hour or so. Well, has everybody had a good conference so far? Yeah. Yes. Yes. So this is my first in-person conference for nearly 3 years. And I've got to say, it's fantastic to to meet everybody in person again, to all be in the same room. It's been a great conference. We're coming to the end, but I've certainly had a great time. I hope you have as well. And actually, this is my first presentation in front of people for quite some time. Done quite a lot on Zoom, but this is my first in front of an actual audience. So I was doing a bit of Googling. I was looking up, how to give better presentations. And one of the things they say is that you should liven up your slides with some pretty pictures. So I went to Google image search and I found this. So this is the Flinders Ranges in South Australia. Right, just Google image search for ranges and found this. I thought this was very appealing. It did take me a little while though, because the first roughly 2,000 results for a Google image search for ranges looked like this. So that was a little less appealing. So I'm afraid I've kind of failed on the pretty picture front. It is just going to be boring slides. But hey, we did get to see the Flinders Ranges, which was very nice. So, okay, today's agenda. What are we going to talk about? So the way this is going to work is we're going to look at 3 relatively simple programming problems, kind of thing you might see in leak code exercises or something like that. Fairly simple exercises. You'll probably be able to look at them and work out in your mind how to solve them. But we're going to use ranges to solve them. We're going to use these exercises as an excuse to sort of dive in and look at different aspects of the ranges library, different things we can do with it, things that you may not already have known. Okay, so 3 problems. The first one we're going to look at is finding the least element of an array. Again, you may already have in mind how you can do that. Problem 2, we're going to look at calculating the sum of the squares of some numbers in an array. Problem 3, this is my favorite. I really like this one. This is string trimming, so we're going to use range adapters to do this. I think this is really great. And then hopefully, all being well, we'll see, but hopefully we'll have some time at the end for questions as well. So that's what's on the agenda. I hope that's okay for everyone, because I really don't have time to change it now. Okay, so let's make a start with problem number 1, which is finding the minimum element of an array. So our problem statement, given a non-empty array of integers, find the minimum value that it contains. So for example, if we're given an array 5, 22, 88, minus 12, and 14, we want to find minus 12. That is the minimum element in the array. So, can anybody think of an appropriate STL algorithm for finding the minimum element in an array? This is not a trick question. All right, I can see one brave hand. Using min element. Using min element to find the min element. Yes, you're absolutely correct. We can use min element to find the min element in an array. It's pretty good like that. So this is how we can do it with the the classic STL. We can call getInput to get our input vector. And then we're going to call min element, standard min element, and we're going to pass vec.begin and vec.end, and that's going to return us an iterator pointing to the minimum element in the array. Okay, so this is how you would have written it for like 25 odd years. This is fine, this is good, this is going to work, no problems whatsoever. Now, in C++20, we can update this. We have new rangified versions of the 90 odd algorithms that are in the algorithm header. We can replace standard min element with the new standard ranges min element. So in all these slides, you'll see this namespace RNG. This is just shorthand for the namespace standard : ranges, just because otherwise it's a lot to fit on the slide. So whenever you see RNG on the slides, It's nothing to do with random numbers, right? It's just an abbreviation for the namespace standard ranges. So, okay, we can call the new standard ranges min element, and we pass it vec.begin, vec.end, and it all works just as it did before, right? Everything's good. But there's another improvement we can make. The ranges algorithms allow us, as I'm sure most of you know, the ranges algorithms allow us to pass a range all in one go. We no longer need to say vec.begin, vec.end. We can just say ranges min element of vec. So, you know, this is something people have wanted for 25 odd years. This is not going to change your life, but it is going to just make things that little bit nicer. So, okay, we can now call min element and just pass it the vector. So let's say you have something that looks a bit like this in your code base. Not exactly this, but something that looks a bit like this. Okay? And days, weeks, months later, one of your co-workers comes along, looks at this and says, well, hang on a second. I'm not using vec after the call to min element. The only thing I'm doing with vec is calling min element on it, right? So why am I bothering saving this thing into a named variable? Why can't I just do this? Why can't I just take the result of get input and pass that straight into the min element call? Okay? Kind of seems reasonable, but if you see this in your code base, or in code review, right, I shouldn't make it as far as your code base, so in code review, this should start setting off alarm bells. Can anybody suggest to me why this should start setting off alarm bells?
Because you have an iterator to a vector that doesn't exist.
Lifetime, I don't know if the microphone picked that up, but you're 100% right. We're going to, on the face of it, end up with an iterator into some memory that doesn't exist. So what's going to happen is that get input is going to return us a new vector, a temporary vector. Min elements is going to do what it does. It's going to find an iterator into that vector. It's going to return the iterator that we're saving into this iter variable. And then at the end of the statement, the end of the full expression is a technical term, the temporary vector is going to be destroyed. And our iter variable is going to be left pointing into some deleted memory, right? So we have a potential dangling iterator. Yeah?
Is it possible to detect that it's R-value and then still returning iterator?
One moment. I like the way you're thinking. Okay. We have a potential dangling iterator, but actually, the question mark is there for a reason. Because in fact, ranges does something quite clever to protect you from this problematic case. Because what ranges does is when you have an algorithm that would ordinarily return an iterator, when you pass an R-value range in, as we're doing on the screen, the return type of that algorithm is adjusted so that instead of returning an iterator, it returns an object of this special type, standard ranges dangling. Okay? So if you pass an L value range in, you get an iterator out. If you pass an R value range in, you get one of these ranges dangling objects out. So this line of code on the screen, this will compile. But I was a bit sneaky. I used auto in the declaration of iter, right? So iter here is actually not going to be an iterator at all. It's going to be one of these ranges dangling objects. So ranges dangling is more or less just an empty struct. It doesn't have any operations defined on it. So creating a dangling object is not a problem, but attempting to use a dangling object is going to cause a compile error. So if we try and do something like this, if we try and dereference the iterator, it's not really an iterator, if we try and dereference the dangling object, we're going to get a compile error. The compile error is going to look like this. Error, no match for operator star, operand type is standard ranges dangling. In fact, this is the exact error message that GCC prints out. So this is actually really good, because this means that when we see an error message that involves this standard ranges dangling type, we know exactly what has caused it. We know that we have mistakenly passed an R-value range into an algorithm. Well, that's not necessarily a mistake. We are trying to mistakenly use an iterator that would have lifetime problems. Okay, so this is C++. We can't protect you from every use of dangling iterators, dangling references. Who knows, one day maybe we'll get like full lifetime bounds checking and all of that. We don't have that, but this is one particular case where ranges does something special to help protect you from potential lifetime errors. And this is very useful. So if we see ranges dangling, we know what the problem is, and we know the easiest solution is usually just to save the input into a named variable so that its lifetime exceeds that of the iterators that are returned from the algorithm. So as I say, ranges applies this dangling protection whenever we pass an R-value range whose iterators can potentially dangle into an algorithm which returns an iterator. However, there are some types whose iterators can safely outlive the thing that you call begin on. So for example, standard string view, or new in C++20, we've got standard span. Well, if you think about what a string view is, a string view just points to some other character array, and a string view's iterators actually just point into this other character array. Okay, so if we have a string view iterator, it is perfectly safe for the string view iterator to outlive the string view from whence it came. So we can do things like this. This is kind of weird, but it's okay. So we've got a string hello world, and then we're creating on line 3 this temporary string view, calling begin on it, saving that iterator, and then the temporary string view is going to be destroyed, but we can still safely dereference the iterator, because the iterator is in fact pointing into stru's character array, and so this is going to be perfectly all right. Kind of weird, but not a problem. So for these types, like string view and like span, we don't need this dangling protection that ranges offers, this changing of the return type into one of these ranges dangling things. So actually, for types like string view and span, we can disable the dangling protection. We can tell the ranges machinery, hey, it's okay, don't worry about it. These iterators are not going to dangle. You can safely return them from an algorithm. And the way we disable this dangling protection is by specializing a standard library trait, enable borrowed range. So we can do it like this. So here's an imaginary string ref type, kind of common thing a lot of code bases have, like a sort of mutable string view. So I've got some imaginary string ref type. And what I'm doing is specializing a variable template, standard ranges, enable borrowed range. And this is going to tell the machinery that this string ref is what's called a borrowed range, meaning a range which doesn't own its elements and whose iterators can safely outlive the thing that you call begin on. Okay, so having done this, having made this specialization, if we then have a function call like this, if we call ranges find, and we pass it what we imagine is an R-value string ref type. So ranges find, like standard find, returns an iterator. If you just passed in an R-value standard string, you would get a ranges dangling object out. But because we've told the ranges machinery, my string ref type is special, its iterators aren't going to dangle. So this call on the screen is going to return an iterator, not one of these ranges dangling objects. Okay? So these things, these types like string view, like span, like this imaginary string ref type, these are what we call borrowed ranges. And they're one way to think of them as ranges that don't own their elements. just refer to some other, just borrow a reference to the other range. So there's one more piece of the puzzle left to mention, and that is views. And I wanted to mention views because informally what you will often hear is that views are ranges which don't own their elements. Right? People will very often say this, and they'll say this actually because once upon a time this was true. Right? Back in the very early days of ranges, this was true, but things have changed quite considerably over the however many years it's been that ranges has been standardized, and the meaning of the view concept has changed quite considerably. So nowadays, it is nothing to do with element ownership, right? You can have views that own their elements, that's absolutely fine. What the view concept is about the copy and move and destruction semantics of the range that you're using. So, as I say, the formal requirements of the view concept have changed many times over the course of ranges standardization, even post-publication of C++20. So the most recent update was earlier this year. It was paper P2415, the aptly titled "What is a View?" By Barry Resden and Tim Song. This was really quite dramatic change to the notion of what is a view, right? It's certainly changed this part of my talk quite a bit. I think it's a good update, but it's changed things quite dramatically. We can now do things that we couldn't do before, but it's better. We avoid a lot of error messages we had before. So this is a good change, and this was retroactively applied as a defect to C++20. So if you are using a very new, or at the time anyway, very new C++ compiler, GCC 12.1, I think MSVC 2022, you're going to have this change. Otherwise, you're going to have the old definition of a view, which prevents you doing a couple of things. But we're going to look at the new definition of a view, what we have going forward. So today, a view is a range whose move operations must be movable, and its move operations are constant time. That is, they don't depend on the number of elements in the range. Okay? So move operations are constant time. If it is copyable, so views don't have to be copyable, but if the range is copyable, then its copy operations must also be constant time. We require that destruction of a moved from object is constant time. That is, basically does no meaningful work, or at least, yeah, does a fixed amount of work, not dependent on the number of elements. But destroying an actual, owning object, that is allowed to be, at worst, order n, n being the number of elements in the range. Okay, so what this means is that standard vector of int is not a view because it's copyable and its copy operation is order n. Right? But a vector of unique pointer of int could theoretically be a view because that is not copyable and its move operations at constant time, a move from object is constant time destroyed, and otherwise destruction is order n. So quite a strange situation where a copyable vector doesn't meet the view requirements, but a move-only vector does. But we can sort that out. Okay, so the compiler can't determine for us the algorithmic complexity of our functions. That's, a halting problem, I think. So we have to opt into being a view. We have to tell the compiler that our range type, or tell the range's machinery that our range type is a view, just as we did for borrowed range. There is another trait called enable view that we can specialize. And we can say, hey, my range type is in fact a view. Or alternatively, there's this standard ranges view base class that we can inherit from, and that will again tell the ranges machinery that please consider this range type to be a view. And there's actually another base class called standard ranges view interface, which we can use instead, which is actually a bit more useful because it comes with some default operations as well. And if you're interested in seeing how we actually write a view, I don't go into it in this talk, but there's kind of a follow-up talk to this one. It's called Conquering C++ 20 Ranges. So you can find that. I gave that at CppCon last year. So if at the end of this you want even more ranges, then you can find that one on YouTube. So today, as the latest changes, we can turn any movable range into a view using a function standard views all. So previously, up until this latest changes, previously this only worked for borrowed ranges. Okay, so previously we were worried about lifetimes and things. Nowadays, we can take any movable range and turn it into a view, adapt it into a view using this function standard views all. So we can do something like this. So we have standard views all, and we're passing it an L value vector. And what this is going to do is effectively it's going to wrap it in an object that just stores a pointer to this vector, right? Because it's an L value, so it's just going to store a pointer to it. Effectively, it's going to return something called a ref view. This is more or less just a reference wrapper with some range operations on it. So it's very cheap to move, copy. It's literally just a pointer. In the second case, we're going to pass getInput as an R value now. And what's going to happen this time is we're going to wrap it in an object called an owning view, standard ranges owning view. And what this is going to do is it's going to assume that you have obeyed the rules and that this thing is constant time movable. And this is actually going to disable the copy operations, right? So the owning view is a move only type. And so the reason for this is to allow you to do things like passing an R value vector, which would otherwise be ordering copy. So we just disable the copy operations, and then we meet the requirements of the view. So this second one you couldn't do until very recently, but this is okay since P2415, and it's going to return you some move only type. And yeah, so the last thing to say is that view adapters implicitly convert their arguments into views using this views all function. Okay, so if we pipe a range into some adapter like this, this first case was always okay. We had an L value vector, and we pipe it into views transform. This was always okay because Vec wasn't going to be dangling. As of P2415, we can use this second case as well. So we're now taking an R value vector, and we're piping that directly into views transform. So this is going to form one of these owning view objects behind the scenes, pass that into views transform. And so V2 here is going to be, again, a move-only object. But this last case, if you've tried ranges in the past, you might have tried to do something like this last case. This caused a lot of pain for a lot of people for a long time. And we have now changed it so you can do this last thing. So this is, I think this is a really good usability improvement. So if you weren't aware that you couldn't do this in the past, don't worry about it. But if you have used ranges before, this is now permissible when it wasn't before. So, okay, what do we start off talking about? I can't remember, it's such a long time ago now. Least element of an array, right? We started off talking about the least element of an array, and we ended up talking about borrowed ranges and about views and about the very latest changes to the ranges library. So, as I say, we're using these little problems just as a kind of jumping off point, an excuse to look at different aspects of ranges. So that's the first one. Let's move on to problem number 2, which is calculating the sum of the squares of some numbers in an array. Okay, so here is our problem statement. Given an array of integers, calculate the sum of the squares of the values it contains. So if we're given an array -2, -1, 0, 1, 2, the squares are 4, 1, 0, 1, 4, and you sum those up, and hopefully you get 10. So there are many, many ways that you could do this with the existing STL. One way that we could do it is to use standard transform to transform each element in place, to replace each element with its square, and then call standard accumulate to sum the elements of this vector. Okay, so first of all, we transform the elements in place, then we sum the vector. So, okay, we've already seen we can replace standard transform with standard ranges transform. And this allows us to not have to type vec.begin, vec.end for the first iterator pair. We just replace it with vec, as you can see on the screen. We do still have to say vec.begin for the output location, because that's an output iterator, so we do still have to get the iterator. But yeah, okay, we've saved ourselves a couple of characters. All right, well, maybe that wasn't so great. But this is a bit better. We can replace, instead of using the eager standard ranges transform algorithm, which is going to eagerly transform each element in place, what we're going to do is we're going to use the standard views transform range adapter. So this is lazy evaluation. Like me, it's lazy. It doesn't do the work until it absolutely has to, right? So setting up the, as you see on line 2, setting up this view basically does nothing, just creates like a holder object to hold the function object. Only in the call to accumulate, as we are iterating over this range, as we dereference the iterators, at the point of dereference, this transformation is going to be applied lazily as needed at the very last moment. As I say, like me, it's lazy, doesn't do it until it has to. So we can write it like this, using this function call syntax, views transform vec lambda. We can also do it like this, using the pipe syntax. So if you've seen any ranges examples online, you will have probably come across this pipe syntax. So this allows us to read our function calls, read our sort of data flow in a more natural way. So here we're taking vec, and then we're piping it through views transform, and then we're piping it through the second adapter called views common. So what is this all about? Well, it turns out that in this particular case, views common is not necessary, but it's a sort of best practice thing. So what we're doing with this view is we want to pass it into standard accumulate. Standard accumulate is a C++ 17 era algorithm, okay? And standard accumulate, like all the C++ 17 algorithms, expects begin and end to have the same type. This is how things always were in the classic STL. In C++20, however, ranges allow us to have separate Sentinel types, dedicated Sentinel types. So it's a bit beyond the sort of time I have available to go into Sentinels too much in this talk, but they can make your range implementations in some cases more efficient. Very often they make range implementations easier to write. Sentinels are a really good addition, but unfortunately C++ 17 algorithms don't understand. So what we have to do is, or what we can do is use this adapter called views common. And what this is going to do is, if our range has a different type for its iterator in Sentinel, it's going to adjust this so that we have a common type, so that we have a common iterator type. It's actually, behind the scenes, it's like a variant, a common type that our C++ 17 algorithms are going to understand. So as I say, in this particular case, it's not necessary because transform of a vector is already a common range. So strictly speaking, we don't need it, but it's good practice when you're going to pass an adapted range to a C++ 17 algorithm, and it does no harm because if the range is already common, already has the same type for the iterator in Sentinel, then views common is just passed through it. It does literally nothing. Okay. So now, instead of using standard transform or standard ranges transform eager algorithm, we're now doing using a lazy range adapter and using that with standard accumulate. So this is already considerably better than we had before, right? Because now we're only doing a single pass over our data in the call to accumulate, whereas previously we were doing 2 passes. Previously we were doing 1 pass to transform everything in place, then another pass to sum things up. Now we're only doing a single pass, so things are better. So that was transform. What can we do about accumulate? How can we update this call to standard accumulate? Well, unfortunately, C++20 doesn't have rangified versions of the algorithms in the numeric header. So if you remember, standard accumulate is one of these algorithms that doesn't live in algorithm, it lives in this other header numeric. So ranges, C++20 comes with rangified versions of the 90-odd algorithms in the algorithm header. Unfortunately, we didn't quite have time to get to the other dozen or so that are in numeric, right? This is rather a shame, but all being well, barring some disaster like I don't know, some global pandemic or something like that, all being well, C++23, this is on track to be in there. C++23 is going to provide us with a whole family, in fact, of different fold operations, fold functions. So this does what standard accumulate does, but it's got a better name if you're familiar with functional programming. So C++23 will be able to use the new ranges fold, but that's in the future. We don't have that yet. So instead, what we're going to do is we're going to write our own range-based version of accumulate. We're going to take standard accumulate and we're going to rangeify it ourselves. Okay, so this is the rabbit hole that we're disappearing down for this little problem. And the reason for this is that I imagine many of you will have algorithms in your own code bases that use iterators, right? C++17 iterators. And so I just wanted to show you an example of how you can update those for C++20. All right, so that's what we're doing here. So we're going to start off with a version of accumulate as it exists in C++17. So this is a conforming implementation of accumulate. Might be simpler than you had thought, I don't know. But you can see what we're doing is we're iterating over our range. So while first is not equal to last, we're going to perform the actual accumulation. So we're going to dereference first. We're going to add it to our existing accumulator and save that into the accumulator. Then we're going to increment first. And then when we finally hit last, we're just going to return our accumulated value. So, okay, this is what accumulate looks like in C++17. So the first thing we want to do to update this for ranges is to support Sentinels. So you can see at the moment we are requiring the same type for first and last. So we're going to update this to support Sentinels. So we're going to add a new template parameter S, and we're going to say that last can have this type S. And you can see that in the body of the function, the only thing we're doing with last is comparing it to first. And this is the only thing that Sentinels are required to do, so required to be able to do, so this is all good. Right, this is fine. So actually, I said this was an implementation of standard accumulate. That's true, but it's actually only an implementation of half of standard accumulate. Because you might know, there are in fact 2 overloads of accumulate in C++17. One of them uses plus, as we've just seen, and the other one allows you to pass a custom binary operation, right? Writing 2 overloads is twice as much work as I'd like to do, so what we're going to do is combine those into a single function, like so. So we're going to take an optional binary operation here called op, and we're going to default that to this standard library function object, standard plus. Okay, so standard plus just calls like operator plus on whatever types you give it. So we're just going to default our template parameter to standard plus, and we're going to default our function parameter to a default constructed standard plus or whatever you pass. And you can see in the body of the loop, we've updated it so that we're now calling this op function object. So this is going to, rather than having to have two overloads, one of which has an extra parameter, we're just going to have just one overload with a defaulted parameter instead. Just saves us a bit of typing. So the next thing we want to do is to gently introduce the use of concepts. So correctly constraining your algorithms correctly is in general a really hard problem. It took literally years to come up with the constraints for all the algorithms in the standard library, right? It's a really hard problem. And it would be a very interesting talk, I think, to have a talk all about how to correctly constrain your algorithms so that they're not under-constrained. That is, they don't allow types that are going to lead to compile errors. They're not over-constrained. That is, they don't reject types that should work. This would be an interesting talk, but it would be, far too long to go into today. So what we're going to do is, for now, or for this talk rather, we're just going to use the minimum amount of concepts that we need in order to disambiguate the overloads of accumulate that we're about to write. So the concepts that we're going to use are input iterator and Sentinel for. So we're going to say I must be an input iterator, must meet the requirements of this standard input iterator concept, and S must be a Sentinel for I. And we can write it like that. We can also write it like this in the template head. This is just an alternative syntax. One more thing we're going to do that's always bothered me about accumulate is we always have to provide the default value for the accumulator, right? We always have to say like vec.begin, vec.end 0. This has always annoyed me. Perhaps I'm just really petty. But because I'm in charge now, I rule the world, or at least I rule this version of accumulate. So we're going to remove the need to specify this default value. We're going to provide a default template argument for the init type. This is going to default to the iterator value type. So this is a new template alias we've got in the standard library. It saves us from having to do all that horrible standard iterator traits, blah, 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 stuff we used to have to do. Now we've got this nice, simple template alias for that. So we're going to default init to iter value t, and then in our function argument, init is just going to be a default constructed, whatever the type is. Okay, so we still can pass a defaulted accumulator if we want to, but by default, it's just going to be whatever the value type of the range is, default constructed. In our case, default constructed int of value 0. All right. So we've got our updated accumulate. Let's go back to our code and start using our accumulate instead of standard accumulate. So this is what it looked like before. We're calling standard accumulate, and this is what it looks like after our changes. Okay. Well, we've managed to get rid of the comma 0 in the call to accumulate, and we've managed to get rid of views common because we now support iterators and sentinels. So, it's a slight improvement, I guess, but it's not much yet. Because what we want to do, really, is not call view.begin and view.end. We want to do what we saw with min-element before. We just want to pass the range as a whole. And the way we do that is by writing a new overload of accumulate, a separate overload that accepts an input range, or in this case an input range, but accepts a range as its argument. So it looks like this. And all we're doing in the body of this overload is we're just calling begin and end and calling the iterator Sentinel version that we've already written. So this is in fact what all of the standard library ranges algorithms do. The versions that take a range, they all just forward to the iterator Sentinel versions. This is literally what the standard library does. So if it's good enough for the standard library, it's good enough for us. So we're just going to write a range-based accumulate that basically just calls begin and end for you and passes that on to the iterator Sentinel version. Oh, you can see that init is now the range value type. So that's the value type of the iterator type of the range. Again, we've got a nice little short template alias for doing that. Okay, so this is where we got to. We can update this so that instead of calling view.begin and view.end, we can just pass view all at once like this, call accumulate on our view. We can write it like this. Alternatively, we don't actually need this view object. If we wanted to, we could just pass it straight into the accumulate call like that. Whether or not you find this more readable or not is a matter of opinion, but we can do it now. It is fine. But actually, there's one last change we can make to accumulate to make things even nicer. And that is to add support for projections. So almost all of the standard library algorithms, the rangified algorithms, almost all of them, at least all of the ones that take custom function objects, they take a new extra optional parameter called a projection. And what projections do is that they modify the view of the data just before the function object sees it. So if you pass a custom comparator to standard sort, for example, or you pass a custom binary operation to accumulate, for example, or to transform, we can basically split this into two, and we can use a projection to modify the value just before we send it to the function object. So unfortunately, I didn't put a link to it in the slides, but Barry Revsin, him again, he has a really great blog post where he goes into some details about projections. So before these slides go out, I'll put a link to it. So I meant to do it, but apparently I didn't. Okay, so we're going to add support for projections to standard accumulate. So this is the way we're going to do it. We're going to add a new template parameter proj, and this is going to default to this new function standard identity. So again, this is what all of the standard library algorithms do. They have this optional parameter, and it defaults to standard identity. So standard identity is just a pass-through function object. It does nothing, right? Just returns what you give it. So our default projection is to do nothing, but we allow the user to supply an optional projection if they want to. And you can see in the body of the loop, what we're doing now is we're dereferencing first, so we're getting the value from our underlying range. Then we're calling proj, this unary projection transform on that, and then we're passing the result of calling proj, we're passing that to our binary operation. So one way you can think of it, and if you look at this, one way you can think of it is that this is kind of like a transform built into the algorithm call, right? It's kind of neat. Projections are great. Like once they're really kind of weird and mysterious if you haven't come across them before. But once you start using them, projections are really very, very useful. They're one of my favorite things about C++20. Okay, so we can add the projection to the iterator Sentinel version. We also add exactly the same thing to our range-based overload and pass that on to the other function. And having done that, we can take our accumulate. This is where we got to. I think this is a little bit ugly personally, but fortunately, now that we can support projections, we can change our code so that we now can do this. So now we're calling accumulate, we're passing in the vec, we're default constructing our accumulator. It's just going to be an int with value 0. We're default constructing our binary operation. Which is just a standard plus object. And then we're using the projection argument to do the transform, right? So I think this is really neat. We can write it like this. Of course, accumulate doesn't return an iterator. All it does is sort of runs through the data and sums it up. It doesn't return any iterators, doesn't have to worry about any lifetime issues, any borrowed ranges, any dangling, anything like that. So we can just pass get input straight into our accumulate call. And so we can replace all of this code we had before with this nice one-liner. So I think this is really nice. And yes, okay, in C++ 17, you could have used like standard inner product or transform reduce or whatever to do that. I'm sure some of you were sitting there going like, come on. But that wouldn't have allowed us to go down this rabbit hole of rangeifying an algorithm. So that's I think is really nice. So I am rapidly running out of time. So we're hurriedly going to rush on to problem number 3. Which is string trimming. Okay. So, our problem statement this time. So, given an input string, construct a new string with any leading and trailing white space removed. So, for example, if we have this hello world with some junk at the front, some junk at the end, we want to remove the junk and just return hello world, right? String trimming. So we're going to use ranges to do this. We're going to start off with just an empty function. This is the function we want to write, we want to fill in. So we're just taking a string, a const reference to a string, and returning a new string as we were asked. So the way we're going to do this is we're going to break the problem down into 2 parts. Okay. First of all, we're going to, in a moment, write a range adapter to actually do the trimming. So this is going to return us some view type, some adapted range. And then we're going to write a function toString, which is going to take our adapted range and transform that into a standard string object, because that's what we were asked to return. That's what the problem statement said we should do. So, okay. Let's turn our attention to the second part, because that's easier to deal with. So what we want to do effectively is write a function like this. We want to take some arbitrary range and we want to transform that into a standard string. So it turns out this is actually a bit tricky to do in all cases in C++ 20. Right? It's a bit of a shame. Right? One way we could do it that works like, I don't know, like 98% of the time is to do something like this. So we take our range and we pass it through views common. So if necessary, we've already seen what that does. It's going to, if necessary, change the return type, change the iterator and sentinel types so that they have a common type. And then we're going to call the existing iterator constructor of standard string. Okay? And this is going to work fine, like, as I say, kind of 98% of the time. There are a few corner cases that this doesn't handle, even after passing things through views common. So in particular, we have move-only iterators in C++ 20. This is not going to handle move-only iterators because the string constructor expects iterators to be copyable, like they always have been. So if you're familiar with range v3, if you've used range v3, you might know of this function that is in range v3 that is called ranges2. And the way this works is that we can put together some pipeline, and at the end we can use this ranges2 thing, and we give it the type that we want to construct. And this is going to, in this case, construct a string out of this adapted range. So this has been in range v3 for many years. It was proposed for C++ 20, but unfortunately just didn't quite make the cutoff. It was a bit late in the process. But the good news is that it's back. It's back, and it's actually quite a lot better than it was in the C++20 era. So the extra couple of years has been good. So ranges 2, again, barring a disaster, is going to be in C++23. So in C++23, we'll be able to use ranges 2. And that handles all the nasty corner cases, so we don't have to worry about it. In the meantime, apologies to any French speakers in the room, but Corentin Jabot, I think is how you say it, who is the author of the Ranges 2 proposal and many other standard library proposals. He has an implementation of this, of Ranges 2 and quite a few other ranges things in this library he calls Ranges Next. So we're going to use this as a sort of polyfill until we have C++23. We're going to use Corentin's library, and we're going to use his version of Ranges 2. So rather than writing this toString function, we don't really need it. What we're going to do is we're going to take the view that we're about to write and pipe that through Corentin's Ranges Next 2 implementation. And of course, we don't really need the extra view object here. We could just use the pipe syntax like that. So in a moment, we're going to write a trim function that's going to return us some adapted range, and we're going to pass that through Ranges Next 2. So all right, we've done the easy bits. Let's do the hard bit. Let's write a trim function. So again, what we're going to do is we're going to take some arbitrary range, and we're going to trim white space from the front and from the back. Okay? So again, we're going to break the problem down into 2. We're going to write 2 functions, trim front and trim back. And what trim front is going to do is going to return some adapted range. And we're going to pass that adapted range into the trim back function. That's going to further adapt the range, which we're then eventually going to return from trim. Okay, so keep breaking our problem down. Smaller bytes makes life easier. All right, next level, let's dive deeper. Let's look at trim front. So again, what we want to do is we want to take some range type in, and we want to return something. Okay. But let's think about what we actually want to do here. What's our goal? Well, what we want to do is we want to take our string, our input range, and we want to look at the first character and say, are you white space? And if the answer is yes, we're going to ignore that and consider this character to be the beginning of our range. And we're going to look at this one and say, are you white space? And if it says yes, okay, we're going to ignore you. Now you're the beginning. Are you white space? Yes. What about you? Are you white space? No, I'm a valid character. So we're now considering this one to be the beginning of our range. Okay? We want to drop elements from the front of our range while some condition is true, while they are white space characters. And fortunately for us, the standard library comes in C++20 comes armed with an adapter that does precisely this. It's called views drop while. So this is going to drop elements from the front of our range while a condition is true. In this case, the condition is using isSpace. This is a C library function, right? It's not very good, but for the purposes of slideware, it'll do. Okay, so what we're going to do in our trim front is we're going to reuse one of the standard library adapters. We're going to use this drop while, and we're going to return the adapted range from trim front. So this is going to return some specialization of drop while of some standard library type. We don't really care. That's why this function returns auto. So we can write it like this. Again, as always, we can use the pipe syntax as well. So we can take our input at the incoming range, pipe it through drop while, and return this adapted range from trim front. So now, what about trim back? So what we were doing before, we were trimming elements from the front of our range, right? So for trim back, we want to be able to do the same thing. We want to start at the back of our range, say, are you white space? Okay, I'll ignore you. Are you white space? Okay, I'll ignore you. Until we find a non-white space character. So in the ideal world, we would have some adapter called something like drop last while that would do what we wanted, right? Unfortunately, this doesn't exist in the standard library. You can write it yourself. It's not all that hard to do. Again, the talk I gave last year at CppCon, I do go through and write this drop last while adapter. So if you're curious about it, you can watch that talk. But we can actually do this in a different way. We don't need this drop last while adapter. We can do this in a different way. Because let's think about what we need to do. We want to drop elements from the back of our range, right? Just as we were doing before from the front, now we want to do it from the back. So what we can do is we can reverse our range, drop elements from what is now the front, and then reverse our range again. Okay? So we can implement trim back by first calling views reverse, then calling views drop while, just as we did before in the forward case, and then reversing again so that everything's in the same order that we expect. So we can compose these three standard library adapters to do the operation that we want to do. So we can put this all back together. We've now got a trim front function that drops from the front, a trim back function that reverses, drops from the front, and reverses again, trim which composes those operations together, and then finally this trim str function that does this in the special case of standard strings. So this is fine. In fact, I really like this code. I think this is a pretty neat solution to the problem. We've got these kind of reusable trim front, trim back objects that's going to work on any suitable range, like bidirectional range of char. Again, we've kind of omitted concepts just for kind of brevity in the talk. But I really like this solution. But we can actually kind of make this a little bit better. So I'm pretty much out of time, so I'm just going to show you very quickly what we can do is instead of writing these function templates that take a range and return some adapted version of that range, what we can do is instead just return the range adapter itself. So rather than taking this R object and piping that into views drop while, what we're going to do is just return a specialized version of views drop while ready to pipe a range into the top of. So we can do that for trim front. We can do that for trim back as well. We can return views reverse composed with views drop while, composed with views reverse. And this is going to return some range adapter ready for us to pipe a range into the top of. Right? So this is really neat. This is really, really powerful stuff. Right? This is like kind of function composition, but happening in C++. It's amazing. So unfortunately, this makes things a little ugly, makes things a lot less ugly if we use the pipe syntax. But we can make it less ugly still. Oh, yeah. We can do the same business to trim. So instead of taking a function object, we're just going to compose two existing adapters. So there's one last little change we can make to make this even nicer, to get our final version, and that is to take our trim front. We're going to zoom back in on trim front for a moment. So what this is a function that always returns the same thing, right? However many times we call this, it's always going to return the same thing, views drop while, like a range adapter ready for use. So what we can do, instead of having a function that always returns the same thing, we're just going to call this function once and save the result in some static lifetime object. And then we're going to realize we don't have to actually have a function call at all. We can just create a static lifetime object that is initialized using views drop while of is space. So trim front here is a static lifetime object. The const expr here refers to the constructor of this function object, by the way. It's not to do with the function call operator, which isn't const expr. This is the constructor. So this is a const expr object, function object, range adapter, ready for use, a specialized version of the standard library adapter. And we can do the same thing with trim back. We can dispense with this function entirely. Now we can just create a new function object that is a composition of 3 standard library adapters. So we do that for trim front, we do that for trim back. We can also do that for trim itself, which is just trim front composed with trim back. And then in our trim str function, which is where we started out, this is what we wanted to write in the first place. And so we're just taking our string, we're piping it through this trim adapter, which is trim front composed with trim back, which is in turn drop while, and then reverse, drop while, reverse. And then we're taking the result of that and piping it through this ranges next to function in order to get the standard string that we were asked for in the first place. And somebody pointed out that actually we can even reuse our trim front adapter in the definition of trim back. So this, I think, this is awesome. You know, I love this. I really do think this is fantastic stuff. This is what makes me really excited to work on ranges, be involved with ranges. We've had to go pretty quickly for this last bit, but I hope I've given you a little taste of what ranges can do and the power of range adapters and things you can do with them. So that's it from me. So thank you very much, everybody. I won't delay your lunch any longer. So.